For over 6 decades, humanity has engaged in a profound and systematic search for intelligent life beyond our planet. We have constructed vast radio telescope arrays to listen for cosmic signals, dispatched robotic probes into the interstellar void, cataloged thousands of exoplanets orbiting distant stars, and scoured the electromagnetic spectrum for any hint of technological signatures, be they intentional broadcasts or accidental leakage. The result of this grand endeavor has been a resounding, universal silence. We have detected no confirmed signals, no verified communications, not even a fleeting, ambiguous hint that another technological civilization exists within the entire observable universe. This persistent absence of evidence is becoming, itself, a form of evidence. I intend to articulate a perspective that much of the scientific community harbors, but is often reluctant to state publicly, a view that contradicts the optimistic narratives prevalent in popular science media. The emerging, unsettling truth is not merely that we have not yet found intelligent life, but that it may be fundamentally impossible to do so. This impossibility stems not necessarily from a barren universe, though that remains a possibility, but from a confluence of immutable constraints dictated by physics, biology, the inherent nature of intelligence, and the sheer, staggering statistics of cosmic time and space. The conclusion that is gradually hardening from decades of data and analysis is that humanity might not only be alone in our galactic neighborhood, but could potentially be the last intelligent civilization within our cosmological horizon, perhaps the last that will ever exist. The probability of us ever making contact with another technological species appears to be vanishingly close to zero. This is a formidable claim that requires rigorous substantiation, as it challenges deeply ingrained intuitions and the optimistic frameworks that have guided astrobiological thought since the mid-20th century. Therefore, I will methodically unpack the logical and empirical arguments, beginning with the foundational Drake equation and demonstrating why each of its parameters is likely far more restrictive than initial optimism suggested. We will explore why the great filters obstructing the rise and persistence of intelligent life are more severe than commonly appreciated, and why, even under the assumption that other civilizations exist, the practical realities of detection and communication render the endeavor nearly futile. The Drake equation, formulated by astronomer Frank Drake in 1961, provides a structured framework to estimate the number of communicative civilizations in our galaxy. It multiplies a series of factors: the rate of star formation, the fraction of stars with planetary systems, the number of habitable planets per system, the fraction where life emerges, the fraction where life develops intelligence, the fraction where intelligence produces detectable technology, and finally, the lifespan of such a detectable civilization. In the early years of SETI, plugging optimistic values into this equation yielded predictions of thousands or even millions of civilizations within the Milky Way, fueling excitement about imminent contact. However, as our scientific knowledge has advanced, through the discovery of exoplanets, deeper insights into abiogenesis and evolutionary biology, and a more nuanced understanding of cosmic and planetary evolution, each term in the equation has been revised downward. The contemporary, evidence-based estimates for these factors are far more constrained than the early guesses. When these revised, smaller probabilities are multiplied together, the resultant number of active, detectable civilizations often approaches one or less, suggesting that we might be solitary in our galaxy, or at least so exceptionally rare that detection is a practical impossibility. Let us examine these factors sequentially. We begin with the most ostensibly favorable terms: star formation and planetary systems. Modern astronomy has confirmed that planets are ubiquitous. Missions like Kepler have revealed that most stars host planetary systems, with a significant number possessing worlds within the habitable zone, the orbital distance where liquid water could theoretically exist on a rocky surface. This suggests a galaxy teeming with billions of potentially habitable worlds. However, this is where the first major constraint emerges. The habitable zone is a necessary but grossly insufficient condition for complex life. True habitability demands a dizzying array of finely tuned parameters, a stable, protective atmosphere with precise composition and pressure, a global magnetic field to shield the surface from sterilizing stellar and cosmic radiation, plate tectonics for climate regulation and geochemical recycling, the presence of a large stabilizing moon to prevent extreme axial tilt variations and climatic chaos, the right orbital eccentricity and inclination, protective gas giants in the outer system to deflect excessive cometary bombardment, and a specific historical sequence of events, such as the delivery of water and organic compounds. Earth's suitability is not merely a product of its orbital position, but the outcome of an extraordinarily rare and specific cascade of circumstances, from a moon-forming impact occurring at just the right angle and magnitude, to the precise positioning of Jupiter, to the persistence of our core-generated magnetic field over eons. Scholars like Peter Ward and Donald Brownlee, in their rare Earth hypothesis, argue that while simple microbial life might be common, the conditions required for complex, multicellular, and ultimately intelligent life are so exceptionally specific that Earth-like planets could be unique in a galaxy, or even beyond. Therefore, the effective number of truly habitable planets is likely orders of magnitude smaller than the raw count of planets in habitable zones. Even assuming millions of genuinely habitable planets exist, we encounter the second formidable filter, the origin of life itself. We have a single data point, life on Earth, and we do not understand the mechanism. Life appeared geologically early on our planet, which some interpret as evidence that abiogenesis is facile given the right conditions. However, we cannot discount the opposite possibility, that we were astronomically lucky. The spontaneous emergence of self-replicating, information-carrying molecules like RNA from a primordial soup involves chemical pathways of such fiendish complexity and low probability that it might be a 1 in a trillion event. Laboratory experiments have successfully produced amino acids and nucleotide bases under prebiotic conditions, but bridging the gap from these building blocks to a self-sustaining, replicating system remains an unsolved leap. It is entirely plausible that the genesis of life is the great filter that explains the silence, a barrier so improbable that most potentially habitable worlds remain forever sterile. If this filter lies behind us, then the number of life-bearing planets in the galaxy could be minuscule. Proceeding with optimism, let us assume life is common and emerges on millions of worlds. The next hurdles are the transitions from simple prokaryotic life to complex eukaryotic cells, and then from multicellular life to technological intelligence. On Earth, life remained exclusively microbial for over 3 billion years. The evolution of the eukaryotic cell, likely via a singular endosymbiotic event where one bacterium engulfed another, might be a freak occurrence of such low probability that it happens only once per galaxy among life-bearing worlds. Without the energy-dense mitochondria that resulted from this event, the evolution of complex, energy-intensive multicellular organisms may be impossible. This represents another potential filter. Furthermore, intelligence is not an inevitable endpoint of evolution. It is merely one adaptive strategy among many, and an energetically costly one at that. For most of Earth's history, intelligence conferred no particular advantage. Out of the billions of species that have existed, only one lineage developed technological capability. This suggests intelligence is a rare evolutionary fluke, dependent on a very specific set of selective pressures, like social complexity, tool use, and language, that may not be replicated elsewhere. When we multiply the probabilities across all these stages, the fraction of habitable planets, times the fraction where life originates, times the fraction where eukaryotes emerge, times the fraction where intelligence evolves, the product can easily fall below 1 for the entire galaxy. But the constraints do not end there. Even if intelligent technological civilizations are somewhat numerous, the issue of temporal synchronization is devastating. The galaxy is over 13 billion years old. Civilizations could have risen and fallen billions of years apart. The window during which a civilization is detectably broadcasting powerful radio signals into space might be extraordinarily brief, perhaps only a few centuries as they transition from radio to more efficient, less detectable technologies like fiber optics. Consequently, two civilizations must not only be within communicative range, a tiny bubble extending maybe 100 light years from their broadcast origin, but must also exist within the same narrow sliver of cosmic time. The odds of such spatiotemporal overlap are vanishingly small when measured against galactic timescales. Assuming we are wrong about all the above and the galaxy hosts many simultaneous technological civilizations, the physics of detection itself poses insurmountable barriers. Intentional interstellar broadcasting requires prodigious amounts of energy to make a signal distinguishable from background noise across light years, with diminishing returns over distance. There is little rational incentive for a civilization to invest such vast resources for a message that will take millennia to reach a target and millennium more for a reply, if one ever comes. Conversely, the accidental leakage signals we might hope to detect, like our own old television broadcasts, are exceedingly weak and become indecipherable from noise over interstellar distances. Furthermore, the search space is incomprehensibly vast. We must guess the correct frequency, modulation, direction, and timing to scan a multidimensional haystack of cosmic proportions. Advanced civilizations might use communication technologies, quantum, neutrino, etc. we cannot yet perceive or have transitioned entirely to forms of existence, post-biological, computational, transcendent, that are utterly invisible to our current detection paradigms. This transcension hypothesis suggests that the detectable technological phase is a fleeting adolescence, after which civilizations evolve into states we cannot recognize. The most somber interpretation is that the great filter lies ahead of us. Technological civilization may contain the seeds of its own destruction through nuclear war, environmental catastrophe, engineered pandemics, or unaligned artificial intelligence. The typical longevity of a communicative civilization may be tragically short, meaning the galaxy is littered with the silent tombs of civilizations that briefly flickered and died. Our observation of silence could be the anthropic shadow of this universal doom. We do not see others because none survive long enough to be seen, and we ourselves are simply in the brief pre-catastrophe window. The implications of our potential solitude are profound. If we are the only or the last intelligent consciousness in the observable universe, then our existence carries unprecedented cosmic significance. Consciousness is the mechanism through which the universe derives meaning, value, beauty, and understanding. Its extinction would not be a local tragedy, but a cosmic vanishing of meaning itself. For over 60 years, a profound and defining human project has unfolded: the search for extraterrestrial intelligence. This endeavor, known by the acronym SETI, represents one of our most ambitious attempts to answer a fundamental question. Are we alone in the universe? We have pointed our most sophisticated radio telescopes toward the stars, listening intently for any pattern, any signal that betrays the presence of another mind. We have built space probes, etched with golden records carrying greetings from Earth, and sent them on interstellar trajectories. We have developed telescopes capable of detecting the subtle dimming of stars as planets pass before them, cataloging thousands of these exoplanets. We have analyzed atmospheric spectra for biosignatures, chemical imbalances that might hint at life. We have searched for technosignatures, evidence of massive engineering projects, artificial light, or structured radio transmissions. In short, we have thrown the full weight of our scientific curiosity and technological prowess against the walls of the cosmos, listening, watching, and waiting for a reply. The result is not a cryptic message, nor a promising signal requiring decryption. The result is nothing. Absolute, unbroken silence. Not a single confirmed, unambiguous artificial signal. Not one verified detection of another civilization's artifact or emission. Not even a persistent, tantalizing maybe that withstands rigorous scrutiny. The universe, for all its hundreds of billions of galaxies, each with hundreds of billions of stars, appears to be a monumentally quiet place. The stars burn, the galaxies spin, the cosmic microwave background whispers its ancient tale, but no other voice joins the chorus. I am going to present to you a conclusion that is increasingly difficult to avoid, one that many scientists grapple with privately but are often reluctant to state publicly because it challenges a deeply ingrained narrative of cosmic optimism. It is not simply that we haven't found intelligent life yet. It is that finding it may be fundamentally, physically, and statistically impossible. This impossibility does not necessarily stem from a universe barren of life, though that remains a valid hypothesis, but from a crushing convergence of constraints. The laws of physics, the brutal statistics of evolutionary biology, the inherent fragility of intelligence and technology, and the sheer, mind-numbing scales of cosmic time and space. The unsettling truth emerging from decades of increasingly sophisticated null results is that humanity might well be the last intelligent civilization in the observable universe, perhaps the last that will ever exist. And the probability of us ever making meaningful contact with another technological species is, for all practical purposes, zero. This is an extraordinary claim, and it demands extraordinary evidence and rigorous logic. It contradicts the hopeful visions of science fiction and the optimistic equations of mid-20th century astronomy. To justify it, we must systematically dismantle the assumptions that have long underpinned the search. We must revisit the famous Drake equation and show why every one of its terms is likely far more punishing than we once dreamed. We must explore the concept of great filters and understand why they are probably far more severe and numerous. And we must confront the logistical and physical nightmares of interstellar detection and communication. This journey will take us from the chemistry of primordial soup to the far future of accelerating cosmic expansion. The destination is a profound loneliness, but one that carries with it a responsibility of almost unimaginable weight. Part 1. The Drake Equation, from Optimism to Pessimism. Our framework begins in 1961 with astronomer Frank Drake. In an attempt to bring structure to the question of alien life, he formulated what is now the most famous equation in astrobiology, the Drake equation. It is not a hard physical law, but a probabilistic chain, a way of breaking down the enormous question into a series of smaller, hopefully more answerable ones. The equation seeks to estimate n, the number of communicative civilizations in our Milky Way galaxy with whom we could potentially make contact. It is expressed as n equals or asterisk times fp times ne times fl times phi times fc times l. Let's define the terms. Our asterisk, the average rate of star formation in our galaxy. Fp, the fraction of those stars that have planetary systems. Ne, the number of planets per solar system with an environment suitable for life, the habitable zone. Fl, the fraction of suitable planets on which life actually emerges. Phi, the fraction of life-bearing planets on which life evolves to become intelligent. Fc, the fraction of intelligent civilizations that develop a technology that releases detectable signs of their existence into space, like radio transmissions. L, the length of time such civilizations release those detectable signals. When Drake and his colleagues first considered this equation at the seminal Green Bank Conference, they plugged in optimistic, speculative values. The result was an n in the thousands or even millions. The galaxy, it seemed, should be buzzing with activity. This optimism fueled the birth of SETI and created a cultural expectation that contact was not a matter of if, but when. Decades later, we have hard data for some of these terms and sobering skepticism for others. Crucially, the trajectory of discovery has been relentlessly downward. Almost every factor appears more restrictive, more demanding than the early optimists assumed. When you multiply a series of numbers, if most of them are small, the product becomes vanishingly small very quickly. Let's walk through the equation term by term with 21st century knowledge. R and FP, stars and planets. The one piece of good news asterisk. We start with the most favorable terms. We now know star formation rates with some precision. More importantly, the Kepler Space Telescope and other instruments have resoundingly answered the question of planets. FP is close to 1. Nearly every star has planets. Furthermore, we have solid statistical evidence that a significant fraction of stars host rocky planets within their habitable zone, the orbital distance where liquid water could theoretically exist on a surface. Extrapolating from our data, there could be billions of such potentially habitable worlds in the Milky Way alone. This is the foundation of the modern optimism. Look at all the real estate. The habitable zone is a misnomer, the rare Earth hypothesis. This is where the first great contraction occurs. Potentially habitable is not the same as habitable, and being in the circumstellar habitable zone is a necessary condition for life as we know it, but is wildly insufficient for the emergence of complex, intelligent, technological life. Earth's ability to support us is not a product of orbit alone. It is the result of a dizzying, specific, and possibly extraordinarily rare confluence of factors. A massive moon, our large moon, likely formed from a giant impact of just the right magnitude and angle, provides extraordinary axial stability. Without it, Earth's tilt would vary chaotically, causing catastrophic climate swings that would prevent the long-term stable conditions needed for complex evolution. Plate tectonics. Our planet's sliding crust acts as a global carbon thermostat and nutrient recycler, regulating temperature over billions of years and creating the geochemical diversity that spurs evolution. A powerful magnetic field, generated by a liquid iron core, this field deflects the solar wind, preventing our atmosphere from being stripped away, as happened on Mars. The right atmospheric composition, a precise, dynamically maintained balance of nitrogen, oxygen, carbon dioxide, and trace gases, forged by life itself, photosynthesis, and geological processes. A guardian gas giant, Jupiter, in its specific orbit, acts as a gravitational shield, deflecting a large number of deadly comets and asteroids away from the inner solar system, while still allowing the early, vital delivery of water and organic compounds. Orbital stability, a nearly circular orbit within a quiet stellar neighborhood, avoiding close encounters with other stars that could destabilize planetary orbits. The list goes on. The right amount of water, enough for oceans, but not so much as to completely drown continents needed for technology. The right metallicity in the primordial nebula, a stable and non-violent host star. Planetary scientists Peter Ward and Donald Brownlee, in their rare Earth hypothesis, argue persuasively that while microbial life might be common in the galaxy, the concatenation of factors needed for animal-grade complex life is so specific that Earth-like planets could be exceedingly rare, perhaps one per galaxy, or even one per observable universe. Therefore, the number of truly habitable planets per system, planets that meet all the stringent requirements for fostering advanced life, is likely orders of magnitude smaller than the raw count of planets in the Goldilocks zone. The billions may shrink to millions or thousands or fewer. FL, the origin of life, the first great filter. Let us grant, for the sake of argument, that there are still 1 million perfect Earth analogs in the Milky Way. Surely life would emerge on at least some of them? Here we confront a profound mystery. We have exactly one data point. Life arose on Earth, and it did so geologically very quickly once conditions allowed. This suggests that given the right conditions, abiogenesis might be fast and probable. However, we must be brutally honest about our ignorance. We do not know how life began. We have not recreated it in a lab. We have simulated the formation of organic building blocks, amino acids, nucleotides, but the leap from a primordial soup of chemicals to a self-replicating, information-carrying system, like RNA, is a chasm of complexity. The probability of even a simple functional RNA molecule assembling by chance is astronomically small. There must be pathways, chemical evolution, mineral templates, hydrothermal vent chemistries, but we do not know if they are likely or freakishly rare. It is entirely possible that the origin of life is a great filter of staggering improbability, a 1 in a trillion event per habitable planet. If so, then among our hypothetical million perfect worlds, perhaps only 1 or 2 ever see life spark in a being. The filter is behind us, and we are the incredible lottery winners. FL could be infinitesimally small. Phi, the evolution of intelligence, not an evolutionary goal. Assume life is common. The next step is the evolution of intelligence. Here, we must discard a persistent anthropocentric myth that evolution has a direction or a goal, and that goal is intelligence. It is not, and it is not. Intelligence is merely one adaptive strategy among countless others, and for most of Earth's history, it was not a particularly successful one. Consider the timeline. Life appears 3.8 billion years ago. For over 3 billion years, it remains exclusively microbial. Simple prokaryotic cells rule the planet. The leap to complex eukaryotic cells, with nuclei and organelles, appears to have required a fantastically unlikely event, one bacterium engulfing another, leading to a permanent symbiotic merger, giving rise to mitochondria. This event may be so rare that it happens only once per galaxy among life-bearing worlds. Then, another 2 billion years pass before the Cambrian explosion of multicellular animal life. From that point, animals diversify wildly for over 500 million years. Dinosaurs reigned for about 165 million years without developing technology. In all that vast time, across billions of species, only one lineage, a specific branch of African primates, developed technological intelligence capable of abstract reasoning and tool manipulation. Intelligence is metabolically expensive. Brains are energy hogs. In the ruthless calculus of natural selection, a big brain is only worth the cost if it provides a survival advantage that outweighs its drain. For most ecological niches, it does not. Simplicity, efficiency, and rapid reproduction are more reliable strategies. Our intelligence may be the product of a unique and non-repeatable cascade of selective pressures. Arboreal life requiring 3D navigation. Social group, living fostering complex communication. The descent from the trees onto savannas encouraging tool use for hunting and defense. Therefore, Phi, the fraction of life-bearing planets where intelligence evolves, could also be vanishingly small. Earth's success rate for producing a technological species from animal life is essentially 1 in many tens of millions of species. This is not a promising ratio. FC and L, the brief window of detectability. Finally, we reach the last terms. FC assumes an intelligent species will develop a technology we can detect, like radio astronomy. But what if their intelligence is non-technological? What if they are like dolphins or whales, profoundly intelligent, social, and communicative, but in an aquatic environment where manipulating fire and metallurgy is impossible? They would never become detectable. But let's assume they do, like us, stumble upon radio waves. This brings us to L, the most critical and perhaps most depressing term of all, the longevity of a detectable civilization. Humanity has been broadcasting detectable radio signals into space for about a century, a mere blink in cosmic time. And already, our leakage is decreasing as we transition to cable, fiber optics, and low-power digital networks. An intentional, powerful beacon aimed at the stars would require a monumental, sustained investment of energy for essentially no practical return, given the 1,000-year delays for any possible reply. Worse, technological civilization seems to carry the seeds of its own destruction. Nuclear weapons, climate change, engineered pathogens, potential artificial intelligence risks. The great filter may be ahead of us. If most technological civilizations last only a few centuries before collapsing or destroying themselves, then L is a very small number. The galaxy could be littered with the silent tombs of civilizations that briefly flickered and went dark. Even if they don't self-destruct, they may simply change. A civilization 1,000 years more advanced than us might use communication technologies we cannot yet conceive of, quantum, neutrino, or might even transition to a post-biological state, uploading consciousness, merging with machines, or transcending into forms of existence we cannot detect. The window where they are broadcasting old-fashioned radio waves we can understand might be only a few hundred years wide. Now, multiply all these terms. Our asterisk times FP, a large number, times a much smaller than it seems, times FL, perhaps infinitesimal, times phi, also perhaps infinitesimal, times FC, maybe small, times L, likely very small. The product, N, no longer yields thousands. It often yields a number that is less than 1 for the entire galaxy. The most parsimonious explanation for the Great Silence may simply be that N is almost equal to 1, that we are it. Part 2. The insurmountable problems of detection and communication. Let's engage in a thought experiment. Let's assume we are wildly wrong about the Drake equation. Let's assume the galaxy is, in fact, home to 1,000 technological civilizations right now. Even under this wildly optimistic scenario, the chances of us detecting them or communicating with them remain virtually zero due to a series of physical and practical barriers. 1. The tyranny of distance and time. The Milky Way is 100,000 light-years in diameter. Even if there are 1,000 civilizations, they are, on average, separated by thousands of light-years. A radio signal traveling at the speed of light takes millennia to cross these gulfs. Any conversation would have a round-trip delay of many thousands of years. This isn't communication, it's time capsule monologue. By the time a reply arrives, the civilization that sent the original message may be unrecognizable or extinct. Furthermore, civilizations must be temporally aligned. A civilization that flourished 50,000 years ago and one that arises 50,000 years from now will never know the other existed, even if they occupy the same star system. Their signals and existence pass through the cosmos like ships in an infinite, dark ocean, missing each other by epochs. 2. The energy problem and the search space haystack. To be detectable across light years, a signal must be incredibly powerful or deliberately beamed. The energy required to broadcast an omnidirectional signal strong enough to be heard over interstellar background noise at a distance of 1,000 light-years is astronomical, on the scale of total planetary energy output. It's an irrational investment with no foreseeable payoff. Conversely, the leakage signals we might hope to catch, like our own old TV broadcasts, are incredibly weak and degrade into noise within a few tens of light-years. Then there is the search space. We must guess the correct star to look at, the correct frequency to listen on, the correct modulation scheme, and the correct time. The sky is vast, the radio spectrum is wide, and we have examined only a minuscule fraction of possible targets. SETI is like looking for a needle in a haystack, but the haystack is the size of a planet, and we've only examined a few specks of dust on its surface. An alien signal could be passing through our telescopes right now. But if it's on a frequency we're not monitoring, or from a direction we're not pointed, or encoded in a way we don't recognize, we would never know. 3. The transcension hypothesis. They've moved on. Consider the pace of our own technological change over just the last 100 years. Now extrapolate 1,000, 1,000,000 years. A civilization vastly older than us would likely be so advanced as to be unrecognizable. Their technology might involve manipulating space-time, dark energy, or other physics we haven't discovered. They might live as uploaded consciousness in optimized computational substrates, having little interest in the physical universe or in broadcasting radio waves to primitive biological beings. They may have transcended into realms or dimensions we cannot perceive. If this transcension is a common outcome of technological advancement, and if it happens on timescales of a few thousand years, then the window during which civilizations are detectable in the radio spectrum, the only way we currently know how to look, is cosmically brief. The galaxy could be teeming with these transcendent intelligences, and we would be as oblivious to them as an ant colony is to the internet. 4. The zoo hypothesis or the simulation hypothesis, unfalsifiable speculation. Some propose solutions like the zoo hypothesis. They are here, watching, but deliberately hiding under a prime directive-like policy, or the simulation hypothesis. We are in a simulation that doesn't include other civilizations. While entertaining, these are philosophically unsatisfying and scientifically unfalsifiable. They are essentially giving up on a physical explanation and invoking unprovable entities or scenarios. Occam's razor suggests the simpler explanation, that they are not there, is preferable. Part 3. The implications of solitude, cosmic significance, and profound responsibility. If the arguments hold, and we are, for all practical purposes, alone in the observable universe, the implications are not merely disappointing. They are existentially transformative. This shifts our self-conception from a young species in a crowded galactic neighborhood to the sole known bearers of consciousness in a cosmos of incomprehensible scale. This realization can initially feel like the ultimate nihilism. We are insignificant, temporary, and our struggles are meaningless against the backdrop of an indifferent universe. But this is a profound misreading. The opposite is true. Consciousness as the source of cosmic meaning. Without a conscious observer, the universe is just a collection of physical processes, particles interacting, stars fusing, galaxies colliding. It has no beauty, no meaning, no value, no story. These concepts only arise within a conscious mind. We are the universe's mechanism for generating meaning. We are the way the cosmos knows itself, appreciates its own beauty, contemplates its own origins, and wonders about its own fate. If we are the only such mechanism in operation, then we're not insignificant. We're the most significant thing going on in the known universe. We are the custodians of meaning itself. The ultimate moral imperative, existential risk reduction. This perspective places upon humanity a responsibility of staggering magnitude. If we are the sole vessel of consciousness, then our extinction is not just a tragedy for humanity. It is a cosmic tragedy. It would be the permanent snuffing out of meaning, value, art, love, and understanding in our region of reality. All that potential future experience, trillions of lives over billions of years, the art and science and philosophy yet to be created, would be lost forever. Therefore, the primary ethical imperative for our species shifts decisively. Our most important project is no longer just economic growth, political dominance, or even solving terrestrial problems like poverty, though these remain vital. Our overriding priority must be existential risk reduction, ensuring we survive and navigate the dangerous adolescence of our technological civilization. The threats are clear: nuclear war, climate catastrophe, engineered pandemics, unaligned artificial intelligence, and other unforeseen technological perils. Managing these risks, ensuring the long-term survival and flourishing of conscious intelligence, becomes the supreme goal. It is the project of keeping the only light in the cosmic darkness from going out, the charge to flourish and to create. This responsibility is not just about survival. It is about flourishing. Being alone means that human culture, in all its diversity, is not just one interesting example of how beings can live. It is the only example. Every language that goes extinct, every cultural tradition lost, every artistic genre that fades, represents a unique way of experiencing and interpreting reality that vanishes from the cosmos forever. Preserving and nurturing this diversity is a cosmic act. Furthermore, every act of creation, a symphony composed, a scientific theory formulated, a kindness extended, takes on new weight. We're not just entertaining or helping ourselves. We are enriching the only repository of meaning that exists. We are adding to the universe's sole catalog of beauty and understanding. The vision, from being the last to becoming the first. There is a hopeful corollary to this profound loneliness. If we are alone because all others have failed, because great filters of self-destruction litter the past, then we have a historic opportunity. We could be the ones who make it. We could be the first civilization to pass through the technological bottleneck and achieve long-term stability. We could be the first to shepherd consciousness safely into the far future. Our mission, then, is to ensure that we are not the last but the first. The first to spread conscious awareness beyond our cradle. The first to seed life and intelligence on other worlds, whether by spreading our own descendants or by creating benevolent artificial minds. The first to ensure that the flame of consciousness, once lit, is never allowed to die, but is instead tended and grown until it illuminates the galaxy. Conclusion: our moment of cosmic choice. The Great Silence is not an empty result. It is a deafening message. It tells us that the universe is not as we hoped. It is not a populated galactic community awaiting our arrival. It is vast, silent, and as far as we can tell, mostly empty of mind. This is the reality we must now confront. It is a reality of profound loneliness, but also of profound purpose. We are the anomaly, the miracle, the unlikely spark in the dark. With that knowledge comes a burden unlike any other. We are the guardians of consciousness. The fate of cosmic meaning rests in our hands. The choices we make in this century about our technology, our planet, and our conflicts will echo not just through human history, but through the history of the universe itself. Will we be a brief, bright flash that fades into the eternal silence? Or will we be the stubborn, enduring flame that learns to survive, to grow, and to finally fill the silence with the chorus of a consciousness that has learned to keep itself alive? We are alone, and therefore we must become the beings who are up to the task of bearing that solitude and transforming it from an ending into a beginning. The universe has given us a question in the form of silence. Our enduring existence must be the answer. Thank you.